Previously, we learned about P81, which is problem 81, where we cut a section and then we see what resultant loadings that we have at the section, alright? Now in P82, what we want to do is, it's already cut, like this problem is already cut here, and then you are given the internal loadings, and then you need to find what kind of stress for each point, for particular points, what kind of state of stress for these particular points, right? So here, in this case, it's cut already here, and then you have this axial load P, right, at the anti-centroid, and then you have the shear force V, right, and then you have bending moment M, okay, bending moment, right, see, and then you have this torsional moment T. Is it okay? So the question asks you to find, actually this is preliminary, but actually you need to understand this before you go to the combined loadings problem, alright? You need to find what is the state of stress at point A here and point B here. Point B at the top, point A at the right, the most right? So let's go to point A first. So first, you need to understand what kind of stresses generated by these internal loadings, alright? This P, V, M, and T. So basically, first, sigma equals to P over V, isn't it? Simple, from chapter 1 and chapter 4. And then another, this is due to P, right? Then one is sigma equals to M y over I, isn't it? Minus M y over I, which is due to the bending moment M, right? That generates normal stress, sigma, bending stress. And third one is tau equals to tau equals to T rho over V, T rho over J, which is, let's put it side by side. Tau equals to T rho over J, which is in chapter 5, torsional moment, alright? Torsional moment T will cause shear stress tau, alright? So this is for T, and the one is tau equals to V, Q over IT, which we just learned in previous chapter, chapter 7, transverse shear, right? Shear stress due to shear force V, right? So we go to point A. At point A, okay, when you draw this point A, you take this, okay, because you cut here, so you draw this surface first, okay, make it cube. This is the surface, okay, and then you make the rest of the 3D. It's okay. What you have to do is first, due to P, sigma due to P. Do you have this sigma due to P at point A? Yes or no? The answer is yes. You remember in chapter 4 we discussed about that. When you apply this, and actually you have your uniform stress for the whole section, right? So you have this. For due to P, okay, you have this internal load P, alright? Is it okay? So plus, alright? Of course, this one will result in sigma, okay? I just want to write P here because it will be easier for you to relate with sigma, okay? I mean to distinguish between P and, for instance, M later on, alright? Next, due to M, okay, sigma due to M. Do you have that one at point A? At point A, do you have that? This is Q, okay. So this is the surface that is facing you here, right? Do you have this sigma due to M? Yes or no? The answer is, this is due to P. Let's put it like this. Okay. Do you have that? The answer is no. You don't have. You know the answer why? Get this bending moment M. Alright? This bending moment M. The neutral axis for this bending moment M is this. Okay, this axis, neutral axis. Right? So you remember from this equation, when y equals 0, which is at the neutral axis, then sigma is 0. So normal stress or bending stress due to M, there is no bending stress due to M at this point A. You'll see later on, for point B you have that one. Okay, for M again, you don't have the stress, internal bending stress due to it, right? So next we go to look at what happened with our T. So what about T with torsional moment? We have the shear stress due to torsional moment T. Alright. Okay. So the answer is yes, because look at this equation for tau equals to T rho over J. The variable is rho, which is the distance from the centroid. So basically rho is 0 here and increase it until rho reaches C, which is the radius. So here for this T, the rho is 0, and here the rho is maximum. So for this you have rho, and the direction of this rho is going up about this surface. It's okay because T goes this way, so it goes up. Okay, goes up at the surface of A. Right? So this is the one, and because of this you have the complementary stresses. Right? For the shear stress you have this, okay, at the top, and then at the bottom you have going that way, and the back side you have going down. Alright, complementary. You have to check this again. How do we do these complementary stresses? Alright, and finally due to PMT and V, isn't it? Finally, for V, do we have this V? I mean, not this V, of course we have V, but do we have this shear stress due to V about point A? So the answer is, okay, this is V, this is neutral axis. Previously for M, okay, for M, neutral axis is this, please understand that. For V, the neutral axis is this, which is perpendicular to V, okay, through the centroid, alright? So if you look at this equation, tau equals to VQ over IT, when you have Q maximum, you can have Q max at the neutral axis, and you have Q equals 0 at this point and that point, which is the utmost distance from neutral axis. Alright? So for point A, your Q is 0. Okay, so V you don't have any. Alright? So these are the state of stresses for point A due to these loadings, which means that for normal stress due to P you have that one, normal stress due to M you don't have, normal stress shear stress due to T you have that one, alright, going up, and the shear stress due to V you don't have that one because it is at the utmost point. Okay. Next we go to point B. This is point A, right? This is point. Now we go to point B. For point B, same thing. I mean same procedure. So you have this P, due to P, you have this due to M, you have due to T, I mean the sequence doesn't matter, alright? And you have this due to V. Okay, as long as you understand what is happening, then that's fine. You can start from any P, M, or T, or V, right? So again, for B, this is the surface, right? Okay, this is the surface, and then you draw the cube, right? Okay, this is the surface. Do you have stress due to P at point B? Okay, this is point B, let's put that way. This is point B. You have stress due to load P. Of course, like what we discussed previously in this one, alright? Though you apply at the center, you assume everything to be equivalent throughout the surface, right? So you have this P at the surface, and of course you have the reaction at the back, alright? You have done this in chapter 1, please understand this by now. Alright, next, due to bending moment, M, again, this is the surface, right? The surface which is facing you for point B, and then you draw the rest of the cube, right? Again, this is the surface. So due to M, what happened? Look at the equation. Okay, sigma equals to minus my over I. Do you have moment? The answer is simple, yes. 0 here, that's why you don't have at A, at this neutral axis of M. But this point, at this point, actually in fact you have C, the maximum, isn't it? So you have this bending stress. Okay, is it tension or compression? For point B, the answer is, in this case, it is tension, isn't it? Because see the direction of M, it goes out at the top, going inside at the bottom, isn't it? Below neutral axis and above neutral axis. So at point B, it is a tension. Alright, this, right? So the black one is the tension, the stress, and then the red one is the reaction at the back. Right? Right? This is for M. And next, for T, for torsional moment, okay. Again, this is the surface. Do you have this stress due to shear stress due to T? The answer is yes, again, like A, but this time around it goes, for A it goes up, for B it goes to the left, isn't it? Okay, so you just follow the direction, the shear stress direction goes to the left, right? Which is this one, is at point B, that surface, and then you draw the complementary shear stresses, which means that at this one, you have this, at the back one, you have this, and at the left hand side you have this. Alright? Okay, finally, due to V. Okay, again, this is the surface. You draw the rest of the cube, right, for the element. So this is the surface. You have, so this, in this one you have this tau due to V. The answer is yes. Okay, because now you have Q. You see, in fact, the Q here is the maximum at the neutral axis of V. This is V. Okay, this is V. This is neutral axis, and because neutral axis of V needs to be perpendicular to it, right? So at this point, this is in fact along this neutral axis, including B, it has the maximum shear stress. The direction will be the same as T, because it goes this way, right? This V. Okay, so it goes this way. 0 here, maximum along this point, and it goes to the left. So you have this, okay, going to the left, and then you draw the complementary shear stresses. Okay. Alright. Okay, now we go to P82B. Alright? Cannot see the problem. It's just the difference is now you cut this way. Okay? So this face is going up. Okay, facing up. And you only have 3 internal loadings here, which are torsional moment T, right? And then bending moment M, and this shear force V. You don't have the V. Alright? So in this case, obviously you don't have this. Right? From these four equations of stresses. Okay, so the first one is, let's look at which one we want to start with. Yes, probably you can do M first, right? So we do point A and then we do point B, alright? So this is for point A. So this is for point A, which is this point. So for point A, okay, due to bending moment M, right? We draw this guy, right? Please remember here, your surface, your A surface is this one at the top, right? Because you are looking from the top, right? You cut, we take this point and this is the point. So this is the surface of A, right? So due to M, do you have bending moment? Due to M, the answer is no. Why? Look at the equation. For this M, right? The neutral axis for this M is this line, right? So along neutral axis, the y is 0. Simple. So you don't have this. No bending stress due to bending moment M. Right? So next, due to V. Right, again, this is the surface of A, right at the top, and you draw the rest of the cube. Right? So for V, do you have V goes this way, okay, goes to the right? Do you have this shear stress? The answer is, look at the equation, look at Q. For this one, for A, you have maximum of Q, isn't it? Because for this V, the neutral axis is this one, right? The neutral axis is this one, so this one, at point A, it is along the neutral axis, so for V, Q is the maximum, right? So you have tau going which way? Remember, not this one is the surface of A, right? Goes along V, right? V goes to the right, so this one goes to the right. Is it okay? And then, of course, you draw the complementary shear stresses. One, you might wonder why I draw the dotted lines. The reason is because the only surfaces here that you really can see is this, and this. Okay, these three surfaces due to this kind of angle, oblique angle, right? I don't know what kind of angle they name it. Okay, so that's why these two, they are dotted lines. They are drawn with dotted lines because actually you cannot see from here, right? Again, next, due to T, alright, draw this top surface first, right? Because the top surface is the A, right? Okay, so due to T, do you have that one? You have this shear stress? The answer is yes. Which direction? Same direction as here, right? Same direction as this V, right? Because tau goes this way, so here, here, here. So this one is same as V, right? And again, you draw the complementary shear stresses, right? Okay, next we go to point B or volume B. Okay, go to B, volume B, right? So for M, bending moment M, this is the surface, isn't it? This is the surface, the top one, right? Do you have bending moment due to for point B here? Do you have bending moment? The answer is yes, because this neutral axis y equals 0, while this one is y equals to C, right? Which is the maximum here and here. So of course you have, and then is it compression or tension? The answer is tension. For M, this is neutral axis, okay? So below neutral axis here, it is tension. Above neutral axis, they are all compression. Alright, so this one is tension, wake up. And at the bottom surface, you have going down. Right? So okay, again, please remember this is the surface. Okay, the surface, the top surface is the surface that you cut for point A and point B. Right? And then we look at V, what happened with the shear stress due to V. Okay, again, this is the surface. For V, you don't have shear stress because here this is for V, this is the internal axis for V, right? And then maximum and internal axis, Q max and internal axis, but here you don't have Q at all. Okay, the remaining area, right? Y bar prime times A prime, right? You don't have that. There is no remaining area, tau equals to 0. Okay. And finally, due to T, okay, again, draw the top surface first. You can draw better than me, I hope. Okay. Again, this is the top surface of point B. So due to T, of course you have, right? For A, this way. For B, it goes that way. Right? So, it goes this way. Isn't it shear stress? Right? And please remember, rho for shear stress due to T, the rho is 0 at the center, but it is increasing up to the circumference, which is rho equals to C at the circumference, right? So for B, you have this. I'm going to draw the commutatory stresses, but I want to show, you see this T, at point A, it goes this way, right? Goes to the, let's say, right. This one, it goes that way, to the back, okay? So this one goes to the right, A, this B goes to the back, alright? So you draw the collimator. On the front surface, you have going down. At the back surface, you have going up. And at the bottom surface, you have going to the front, right? Okay, this is for internal loadings. Sorry, the state of stresses for internal loadings.